Alright, in this video I'm going to be doing number 3 from the Midterm 2 review. And before we get started, I do want to say that I am using the TI Inspire CX2, and something that I recommend everyone does that has this calculator is to set your complex number I as the letter G on the keyboard. So the way to do this is you select this pi symbol and you go to find I, you enter that, and then in the same bar you go to control var, because then you get your stored value, and then you just select J, and then you click enter and it will return this I value. So every single time you click J, every single time you click J, you should get I in return. And something that you should do, or you should make sure that you do, is between your J and the number that you're multiplying it by, always click the multiplication symbol, because if you just write J30, it will register this as a string and not as a number times a number. Yeah. Alright. So in this problem, it states, the circuit shown operates in steady state. Find the numerical expression for the current I sub q of t. And we are given v sub s of t, and we're given I sub s of t. So the very first step is to find the impedances. So we can do this by converting our inductance using j omega L, and our capacitance using negative j over omega c. So I went ahead and redrew the circuit just to make it clearer for me. It's not a great drawing, it's just a little sketch. And so what I did here is exactly what I said. So you do J times 30, which is given here. And take note, the very first thing you should look at is the fact that your voltage with respect to time and your current with respect to time both are in the same both have the same angular frequency. So that's going to be very useful later. But for now, to find the impedances, you just go ahead and plug that into your equations. And take note that what I do with the capacitance is I don't keep it in terms of microfarads, I just have it as times 10 to the negative 6th. And so you get, for your inductance, you get your impedance as J99 ohms, and your capacitance as negative J times 59.52 ohms. So the next thing that I'm going to do here is move along with the node voltage. So I have set this top node as Vx of t. I'm just going to rewrite over it just so you know what I'm referring to. I should probably highlight it, but that's alright. So on this left wire, we can see that we have our Vs of t oriented positively and our dependent source oriented negatively. So we can have Vs of t minus 50 times I sub x of t is equal to Vx of t. And then what we can also do, sorry, I'm not sure why it's not moving. Something we can do is that we know that through this wire, we know that the voltage across here is our Vx of t. So we know the impedance through here now from our previous step, so we can multiply this by our Ix of t since we know the current there. So now we have two equations in terms of Ix of t. We can set these equal to each other to find Ix of t, since we do have our Vs of t value given in the problem statement. So when we set those equal to each other, we get Vs of t is equal to 50 times Ix of t minus J59.52 times Ix of t. And we can just do some algebraic manipulation and get I sub x of t is equal to vs of t over 50 minus j times 59.52. And what I did here is I converted it into polar just to make my life a little bit easier. And I converted the bottom to polar. And then we get this as our I sub x of t. And remember that we want to find our I sub q of t, and we've already found I sub x of t. So what we can do is use our vx of t equation from before and substitute our new ix of t. There we go. So I just restate it, and I restate my ix of t, substitute it in, and that is our new vx of t. And I convert this into the actual equation just because our other two equations are in the same form. And then for iq of t, we have 0 minus vx of t over j times 99. And we get this from this section right here because we know that that's where our iq of t lives. And we know that our impedance there is going to be j times 99 ohms. So we have our voltage and we have our impedance, so we can go ahead and find iq of t, just as we'd find the current of any other given node, or wire, apologies. And plugging that in, you get 0.387 with an angle of 72.97. And you can convert this back into the waveform using your cosine. And we already have 30 as our angular frequency because we've stayed consistent. And we subtract 72.97, that's the angle, and that is our final answer. Thank you so much.